So welcome to your 7th class in Applied AI, which is our 4th time together, right? After this, next week you come to a midterm exam, and afterward, my part will be given over to Gongkan, who's my right-hand man. He's been with me since I was working in the bank, Siam Commercial Bank. Okay, he's gonna take you through the agentic workflow. I'll explain to you what that means in a while. Okay, in a bit. Okay, so let me start by saying, what are we talking about today? What are we talking about today? Okay, if you recall our first lecture, oops, let me make it a little bit bigger. Okay. First lecture, right? It's about AI. In particular, how we got here. So it's kind of like techno, historical context. Okay. So basically how we got to today's AI. Okay. And the definition of AI. So that would be the first lecture, right? The second lecture is about the intimate relationship between machine learning and AI. Okay. In particular, I already told you that AI cannot be built as a if-then, right? Well, it could be, but the if-then code would take infinitely long codes, right? Infinitely long set of if and infinitely long set of then. So it can't do that. Can't do that. So instead, AI has to be some kind of algorithm that learns some kind of F from some kind of X. Okay, right? So that's what we mean by machine learning. Okay. And we talk about the 3 basic paradigm of machine learning, which basically mimics how human beings learn, right? So the unsupervised learning process that you do as you're empowered with your sense perception, you can see things, you can hear things, you can smell things, you feel good, you make an association, say your mom with the nice feeling of warm milk, whatever, right? And maybe the sight of a dog with a large jarring barking sound. So this kind of auto association that you learn in an unsupervised manner. Nobody told you what to learn. In fact, your parents have no control over what you learn in this sense. So that thing here is about unsupervised learning. Okay, unsupervised learning. I'm just going to put UL, right? And then in a more formal, not formal, but right away, as soon as you begin to understand preliminary basic of language, the way your mom would teach you vocabulary is to say, okay, this is an apple. Say it, okay, and you say apple, good. You say orange, no, not good, okay? So there's right away immediate correction, right, between right or wrong answer. So this kind of very super process of what you learn, what is right and not what's wrong, that's called supervised learning, right? And finally, the third mode of learning, which is important to human being and therefore mimic in a machine learning environment, is reinforcement learning. You know how your behavior affect your environments and how the environment, in particular, I'm talking about your kindergarten classmate and your friends, right, and neighbor, give you feedback, right? And this feedback is not immediate. So if you go to kindergarten and you start, bullying your friends, you don't necessarily get negative comment right away. If your teacher caught it, yeah, then she would do supervised training, which is, no, Johnny, don't push your friend or whatever. Okay. But even if your teacher didn't notice that right away, and you did this over time, and you become a bully, you don't contribute, you show up late, all kind of antisocial behavior, your friends is not going to reward you, going to give you funny looks, right? Start with funny looks, and eventually you don't have any friends. So these are kind of longer term evaluation loop. Now, that's called reinforcement learning, right? Reinforcement learning. Now, I did mention almost right away that reinforcement learning would not be covered if it, in my data analytics class, for example. I write the book about data analytics using machine learning. When I say machine learning, I only cover unsupervised learning and supervised learning. So this thing, even though it is relevant to AI, and in fact, it's becoming more relevant right now. No, because it's more mature in such area as robotics, where you have this long-term evaluation, right? If this robot vacuum cleaner keeps bumping into things, or if you autonomous robot keeps dropping things or falling, okay? So that's kind of like not now. So that's so the third lecture, which is our fifth class together, right? I focus then on this track. But first of all, I say AI. I kind of make a rough distinguish grouping into predictive and generative. Okay, right? And the predictive is still going to cover a large chunk of your AI lives, right? It's going to be very much the tools of the trade for a long time. And so this predictive AI, basically, it's about verifiable ground truth. So there's something about accuracy. There's something that you can verify, say, yeah, this is good, correct, this is not correct. Okay. So even if it's unsupervised learning, there is an idea of correctness or something that's grounded in real data, real empirical data. Whereas with generative AI, it's rewarded based on creating plausible context relevance, right? Like I said, like a ChatGPT, for example, it can give you completely wrong answer, okay? But there are two kinds of wrong. So I said, how are you? What year is it? What year is it today, right? So if it gives you 2024, it's correct, okay? If it gives you this year is 2050, that's wrong, okay? But it's wrong in a context correct way, because you're asking for year. So it's giving a year. It just gave you the wrong year, okay? What year is it? It's 1980. It's the wrong year, but it's the right answer, okay? Whereas if I say, what year is it today? Banana. Okay, that's definitely wrong in the context sense. It doesn't make any sense to say banana when I ask you what year it is, right? So in that case, generative AI has to be right in the context sense. It doesn't have to be factually correct. It doesn't have to be factually intelligent, okay? So the same way, I ask a child to say, what's 3 plus 4? And a child before kindergarten say, oh, 3 plus 4 is equal to 800. Well, that's still wrong, okay? But at least it's giving you a number, okay? It's not 3 plus 4. What's 3 plus 4, little Johnny? Apple. Okay, that's even worse kind of response. So generative AI is more about plausible context relevance, okay? And then I focus on the predictive AI in particular. So last week, particular focus on this, right? As an extension in a way of what you would have done in high school when you did regression analysis. Okay. Regression analysis is just an equation, all right? It comes in with a formula for estimating the intercept and the slope, but you can think of it as a supervised learning process, right? Given this initial slope of 0, intercept of 0, how would y be predicted given x? Well, it gets all kind of wrong answer, because it moves a little bit, adjust the intercept, maybe move up and down, adjust the slope, positive, negative, and see if the error of prediction goes down, right? So it's moving in the direction that lower the error. So in a way, that's like your child learning to identify apples as apple and orange as orange, okay? So today, okay? Today, I'm gonna continue this journey, but this is the aspect I'm gonna focus on, okay? And you will see that there's a nice sort of like launch pad from what goes on in unsupervised learning to introduction to what generative AI, in particular in the form of large language model GPT is doing. Okay, so that would be like the last bit. And like with yesterday's class, if there is time, again, I want this class to be very hands-on. So you do this collab, you do all kind of stuff. But if there is time, maybe I'll come back for a fifth lecture that sort of like looks under the hood. Maybe. Okay. It has to do with this generative AI, in particular chat or GPT, large language model, stable diffusion, all kind of stuff. Sort of like looking under the hood. Okay. So that we'll keep that as optional. That's today. Now, in general, you guys are actually better off than your previous section because it's the first time I'm trying the material. So what kind of went well and the order of presentation that went well or didn't go well yesterday, I would use it to adjust today's lecture. So usually I would say that your lecture is probably a bit more coherent relative to your type of audience because I guess it was try once and adjusted from yesterday. So the game plan here that I found would probably work if I basically focus on this thing for like maybe 2/3 of the class, right? Half of which on the board conceptually and half of which I would start using the programmatic code, basically, chapter 5, I think chapter 4 or 5 of this thing. Okay, and then we'll start talking about generative AI stuff. Okay, so right, let's start with a little introductory sentence. In my very own book here, okay, a bit of a plug, data analytics. The idea is I view data as some sort of raw material. Okay, so the purpose of data analytics, which I said in my book, is to turn data, distill it for information, right? Then from information, you get insight, and from insight, you make optimal decision making, better decision, basically, right? So whether it's through interactive visualization, probabilistic modeling, or machine learning methodology, it's that kind of journey. It's that kind of journey. So it's a bit like if you think of mining, right? First you have like earth with bits of diamonds in there, and you mine it for diamond. But once you get diamond, it's still not the most expensive thing yet, right? You then send it to the gem cutter, then becomes a cut diamond. Or even better than that, better analogy would be things like petroleum, right? So you're talking about something underground, then you get the crude oil, but then crude oil itself is not that valuable. It goes through refinery process, right? And that's when you separate into really good stuff, like you got benzene for your car, you got polymer, your basis of plastic for making plastic. Then at the very bottom, you have, very crude things like asphalt to make roads and stuff like that. So it becomes more valuable as you go on along. Okay. Now, when I said turn data into information, okay, usually Think of what you mean by what do I mean by information? You know, so if you close your eyes, I say information. You think of it as a piece of knowledge, a piece of understanding, a piece of something, right? So there is something that's kind of extra. Okay. However, because I said everything starts from data, that information can be plucked out of nowhere. It has to be contained in data. In fact, that's what I mean when I go through this thing called digital transformation, when I help give presentation or talk to corporates or banks about digital transformation. The idea is that because you have digital interface with your clients, you generate data, and those data, in a way, is your asset. Okay, you're sitting on it. So as long as you don't throw it away, it's like you have a mountain that's got diamonds in it, or you've got right to a oil reservoir. You haven't tapped into it, but you own it already. Okay. So it's the value of the information has to be in there. Has to be in there. Okay, has to be in there. Now, I often said, and I keep saying this in my class, in data analytics class, there are only two types of information that you really want. Where are the X's? Where are they? Okay. And if I know X, can I know Y? That's it. Thus, the answer to that basically is the information. Okay. The information I'm talking about is basically answer to one of those questions. Now, yesterday in my data analytics class, we talked about probability model. So what it means is we have a mathematical description of, well, you know, X kind of lives here. Okay. So you're most likely to find X here than here, right? And then you do all kind of like mathematical inference. Where's the mean? Where's the standard deviation, skewness, or kurtosis, heavy tail? Now, these are all statistical property. They're all mathematical functions that derive from this mathematical function. Okay, and that's what people if you have a friend who studies undergraduate in statistics, that's their lives, right? Their life is to start with this kind of model, right? And they go to real data. So you can think of data as some kind of like histogram, right? You select the shape that match the histogram, but the shape itself is like the shape of the shirt, right? There's some parameter, the width, the height. So you have to say, okay, is it a little bit taller? Is it to the right? Move to the right, move to the left, squeeze in, squeeze out. And then you get this kind of thing. It's called fit, right? So that's called parametric estimation, because once you choose this type of the function, that shape, you choose the parameter, okay? So you have to choose the right one. If you chose something like this, then there's no way you can get it to work, okay? So you have to get the right function. Once you get the right function, then you can tweak it so it has the right shape. Okay, it's like, yeah, here's a man, I'm gonna fit a skirt. That's not gonna work, right? So here's a man, I have to fit trousers. And then how long? It's inseam, the width, and so forth. Okay, so this is no good. Okay, so and just to complete the sentences, the rest of statistics is a little bit like that problem, fitting, parametric estimation, but there's also like the inverse problem, which is like the example would be a factory claim that it releases pollutant no more than 7 parts per million, right? But because of randomness, if an inspector comes and sample the water on that day, it may get 7.1. Does that mean that that factory should be fine? Not necessarily, because there's some probabilistic deviation, right? But if instead of one day coming in and get 7.1, the inspector comes in for 50 days and take the average, it's still 7.1. Now that doesn't seem excusable, right? Or even if he comes for 5 days, but the average is 50 as opposed to 7.1, definitely not likely, not believable. So it's not about parametric estimation as about testing. testing the claim on the range of parameter, okay? In this case, the parameter is the mean pollutant output, okay? So the claim is mean pollutant output is less than 7 parts per million. And if the statistician collect the data and say, that's not good, okay? I can't give you benefit of a doubt. Basically, it's a benefit of a doubt game, okay? Benefit of a doubt game. So, you know, if you promise your mom you're gonna, you know, go to school and go right home and not stray, right? And one day your mom see you sort of like closer to shopping mall than your BTS or something. Maybe one day it's okay. But if every single day your mom runs around and see you, you know, on the doorstep of a shopping mall or something, whatever, then it's not that believable. So statistical, this is called inferential statistics. Okay. So there's kind of descriptive statistic to basically describe the shape. There's a parametric estimation, come up with the red line, and there's a inferential statistic, kind of like testing the claim on the parameter, okay? The parameter is claims here, but you find some data over here. Is it just chance or really it's consistent, okay? So it's kind of like that problem. Anyway, so the whole premise of all that is about finding where data is. That's your insight. That's your problem. You want to know where things are. That's it, okay? However, if your insight is, and again, I'm going to go to your friends who is from statistics department. If I know, if I have X, what's the best guess of Y? All right. And it turns out because of past data, it's like this. So you kind of like estimate that. That is exactly what this thing does, right? So you don't know what X is, you don't know what Y is. But if you had enough history of X and Y, you can be informed about how they relate to one another. And if you're informed about how they relate to one another, plus you're also informed about what a particular X you are interested in is, you can go over here and say, that's what my Y is, okay? All right. So 3 things has to happen. You have to have the data, and that data through this regression equation inform you of how X relate to Y. That's one piece of information. The other piece of information is, what's the X that you're interested in? Okay, I'm interested in this X. Okay, so this is basically 2 things that you want to know. Now, let me just add a little bit of notation so you know that this thing is also applicable to what we call autoregressive problem, meaning if X is humidity, temperature, barometric pressure, and Y is likelihood of rain tomorrow, okay? So X and Y. But if X is today's rain, yesterday's rain, the day before's rain, whether or not it rains, right? And use all that to predict whether or not tomorrow is going to rain, then it's going to look like this, except Y would be something like XT plus 1. Okay, whereas X would be something like XT and then XT minus 1 and so forth. Okay, in this case, it's called autoregressive. So you look like X predicting X, but actually, technically, the X that you predict is not the same X. Okay, so X today and X tomorrow, you think of X today as X, X tomorrow as Y. Okay, so that's it. I'm saying that these are the basically, you know, from my data analytics class, that's basically the majority of the insight you want to get, right? Now, obviously, from our class, starting to use many colors now. From our class, this was something that can be learned by using the X-Y pair. So that corresponds to supervised learning, right? Supervised learning, given X, this is Y, given X, this is Y, given X, this is Y. Learn the association, I give you a new X, give me a new Y. Okay. End of story. Simple. Now today, okay, but of course with AI, with machine learning, right? I showed you the picture last 2 weeks ago. It's not something like this. It's more complicated. And it's not just one X, it's plenty of X. It's like 500 X to predict one Y, okay? Example I gave was, I think 8X to predict one Y, which is house price, or 4X, which is the measurement of flower characteristic, and the Y is identification of what flower species. I think I did that example, right? Okay. So obviously you're doing this, but a lot more complicated, very complicated. And that's why I talk about this thing called, I hope I did, but remind me if I didn't, this thing called Shapley explanation, right? You don't know how, you can't read the regression equation y is equal to 7x1 plus 8x2 minus 35x3, right? Those are coefficients are easy to read. But if you say y is a function of a bunch of x, and you don't know what exactly that function is, it's a little bit like a black box. Well, one way to do it is to say, well, what if x1 isn't there? How's the rest of the model going to behave? Okay. What if x2 isn't there? What's the rest of the thing going to behave? Okay. So if x1 isn't there, or if x1 is represented as an average, it's a base of individual, for example. Okay. So it's a lot more opaque. Okay. But it does this. Likewise, today. So this is AI methodology using supervised machine learning. So now we're going to do sort of like AI kind of thinking, but in an unsupervised methodology. And so you'll see that you're going to still ask questions like, where are the X's? Where are the X's? This is kind of location problem. Okay, where are the X's? Except you will not be producing a mathematically precise distribution of where the X is, but you do some kind of a little bit more messy description, messy characterization of where data is. Let me give you an example. Let's say you are the data point. Right? Your data point. And each data point, let's say you are x1 and x2 because you have two coordinates, left, right, front, back, left, right, front, back. Okay. So each one of you has two number. You are a coordinate. Okay. Imagine in statistics, it will be something like, where are you guys? And then I describe a mathematical equation, a mathematical expression. So let's say you are all huddled in a ball. Okay. So you huddle in a ball, or you are huddled in a circular pattern, very dense in the middle and a little bit thinner toward the end. Or I can describe you, if I look on, from the ceiling, if I look down, I don't see a ball, but I see an ellipse, something like this, right? So again, it's mathematical definition, right? Mathematical. So it's a bit like this, right? So let's say this thing is 2-dimensional. You can see that, I can see that it looks a little bit like a turtle, right? Turtle, 2-dimensional turtle, okay? So more concentration along this line, spread out here and spread out there. That's a mathematical description. So that would be like multivariate extension of distribution, so multivariate distribution. Today, we're also going to do this kind of thing, but it's messier. Okay. So right away, let me tell you this. You only want to use AI-based description if traditional statistics, probability, mathematical model doesn't fit. Right? In other words, if I walk in here and you guys are huddled in a ball, I'm not going to use AI to describe where you are. I'm going to use a mathematical definition for a circle. Right? If I walk in here and you guys are huddled in a kind of ellipse kind of distribution, I'm not gonna use machine learning, AI, unsupervised learning to describe where you are. I'm gonna actually draw mathematical ellipse, right? So when the data satisfy those properties, and this is where, you know, this estimation, inferential statistic comes in. When they satisfy that, that's what you do. So AI methodology or machine learning methodology in this case, to be specific, in a way arises out of desperation. Okay. It's like saying, if I can predict rain tomorrow from rain today and yesterday using linear regression, I would do that. I definitely would use linear regression. There's no point in me using deep neural network because it's complex, it's opaque, it's hard to understand. Same thing here. If I can come here and say, where are the data point? Oh, that data point is around the circle bundle. It's much nicer to say. Okay, it's clear. The word is powerful. It's more powerful to describe the data that way. But because I walk in here, and let's say I'm looking from above and I look at distribution of data point, I don't see that. I don't see that. In fact, if I'm going to look down, I'm going to see the shape that looks a little bit like, I'm just going to make this up. Let's say this is the shape of a kidney and this is the shape of a banana. That's the example I used yesterday, so I'll use it today. So I look down and see you guys are gathered in a kidney shape and in a banana shape, right? There is no general formula for banana. There's no general formula for kidney. So when the problem doesn't lend itself to very nice, very clean mathematical description, okay, the problem goes from your friend in statistics department to your friend in machine learning or computer science, okay? And that's where we are today. So it's going to be messy. It's going to be, where are data? Where are the points? Where are they located? But in a very messy setting. Okay. Now, take picture. Now, there's yesterday was a little bit awkward because I was kind of moving back and forth between screen and this. So I've decided not to do that. But I'll tell you what you should do is go home. Okay. There's a website called ETYM, ETYM online. Okay. .com or something, I think. Okay. What it means is etymology. That just means where words come from. Okay. Look up the word information or inform. Anyway, it's good fun. But the gist I want you to come away with would be this. When I ask you to close your eye and say, what's information? You think it's a piece of information. It's some kind of knowledge, okay? My friend's phone number is so-and-so. Thailand has this many people. The last COVID has many cases. You know, that sort of information, okay? Well, when you go to this website, you realize that, well, actually information, the very original meaning is a little bit like putting things in the form. Okay, so in like a medieval Europe or something, right? When the sheriff informed the peasants that they have to pay this many guineas for this land or being taxed by the number of windows or whatever, it's telling you to behave in a certain way. Okay, it's actually it's about informing. If you're talking about pieces of knowledge, it's knowledge about the law that the sheriff is gonna apply to the peasants or something like that, right? So it's about, yeah, putting things in the formation. Okay, so when you're talking about inform, okay, if you think of the whole thing, you think it's a piece of knowledge, right? But I want you to think of two things. How about, again, like the sheriff telling the peasants what to do. Okay, you line go over here, you go over there. It's basically putting your subject information. Okay, this is a group of peasants here. You have to pay me so much for the cows, and you have to pay me for milk, whatever, for the land of using the information. Okay, in particular, you can say put it things in the form. Okay, so what is the form? Form is basically the shape, right? So today, when I come in and I say, where are the students? The information is not particular knowledge of where they are. It's a particular understanding of the shape they are in. Okay? Information about the data. Okay? Now you're talking about statistic, right? Information about data. Well, what's the mean? What's the standard deviation? What's the kurtosis? What's the skewness? Huh? That's statistical information. But in our sense, let's think about form as in the shape information. Okay? So the information about where you guys are is what shape are you in? It turns out that you are in kidney and banana shape, because that happens to be how you sit today. Okay? You sit in a kidney shape, you sit in a banana shape. If I look from the ceiling. Okay? So inform is about, so today again, remember, I'm not trying to say if I knew X, what's Y? That's last week, right? What I want to know is where are the X's? And this is answered in the form of what shape do they form in this two-dimensional space? Okay. So information in this case, let me say it again, is about what shape do the data points form in their data space. Okay. In this case, it's two-dimension. You form a two-dimensional picture of a kidney and a picture of a banana. Okay. So that's what we're talking about. Okay, so let's do this. Let's do this, okay? Right. Now, I want to make sure the objective of the exercise is to literally know where you are. Okay, where the data are. So let me do this. Let me do this. Let me just draw two situations. Okay, this is one situation. Okay. This is another situation. Okay. Okay. All right. Now, what I intended to draw was exact same location. And in fact, this would be location of where you guys are sitting right now. Okay, that's right. And the question is, what shape are you sitting in? Okay, now, what I want to do is for you to look at it and say, hey, that looks like, I'm apologize. Maybe it's a liver, it's not a kidney. Okay, but I'm just gonna call it kidney because I've been using the word kidney. And this thing I'm gonna call banana. Right? So what shapes are data in? Well, data don't fall into one shape. Data fall into two shapes. One shape is a kidney, one shape is a banana. Right? So two shape. So basically, if I have X1 to X, say 30 student, I'm going to put some of them in the first group and some of them in the second group, okay? Because it's not ordered, right? So maybe X1, X2, 3, 4, 5, you know, you see what I mean, right? So From this total set, I separate into two groups. Huh? Now I'll start using the word cluster. Cluster usually means something that's kind of like bunch up in a circle. Well, you can generalize the word bunch up in the shape of a banana. Okay, so I separate the original data. Okay, so again, statistics, we come in and say, hey, where are you sitting? Oh, you're sitting in a circle, you're sitting in an ellipse, right? Nice mathematical shape. You don't have a nice mathematical shape, I'm not going to deal with you. I'm going to send your data set to a data scientist who is not a classical or traditional statistician. Data scientist is going to use some technique that we're going to talk about and say, where are the data? There's no nice mathematical description, but I can put them in shapes. Okay, and in particular, I can't put them all in one shape. I have to put them in this case, two shapes. And that shape is the organization, basically it's a partitioning, right? So X1, X2, X3, X4, X5. So basically I just kind of like put them into two groups, right? And this is what we're doing today. Now you will notice that last week, I also mentioned this thing perhaps about separating the line separating blue from red, right? The difference between this case and that case was this was a real label. Okay, it would be something like oh, okay, here's an analogy would be something like this. You Basai, you're a first year student, but last year you were a high school student, and we get two high school coming to Basai. And because you're not that friendly with each other yet, so you kind of sit together based on where you came from. Okay, to make it even easier to make the analogy, one is a boys' school, one's all girls' school. Okay, so the first day nobody knows whom. Okay, so all the boys from the same boys' school sit here, all the girls from the same girls' school sit here, right? Question is, what came first, where you sit or the sex? The sex came first, right? Okay, so before you walk in, you already know you're a boy or you're a girl. Are you from this high school, from that high school? Based on that, a boy sit here. Based on this, the girl from this school sit here. So this label came intrinsic to you. Okay, so you have this notion called label, which is blue or red, boys or girls, right? My classification problem, which again, in your biology friends will call it identification problem, is to create some kind of partition, right? So that if you're on the left of that partition, I call you boys. You're the right of that partition, I call you girls. And in three-dimensional, how would we do this? We saw that in the demonstration, right? In my textbook, you're going to use this kind of like shape that kind of like, you know, elevate one group. So this one would have the value of 0, 0, 0, 0, 0, and this one would have value of 1, 1, 1, or whatever. Sorry, I draw it the other way around. Okay, so there'll be some kind of like downhill and uphill, right? So that is a classification problem. Now is that unsupervised learning? It's not, because the label tell you the truth. The label is girl, boy. The label is 0, 1. The label last class was Certosa, Virginica, and what's the other one? It's the third. But yeah, that one. Okay, right? So that, you know, same distribution, but now that has label. That's why this problem is a supervising, right? Because X is X1 and X2. Y is the label 0 or 1. This is what you want to do. Okay, that's what you wanted to do. You want to create a partition that naturally separate the people you know are designated 1 and people you know are designated 0. Okay, And 1 and 0 is like apple and orange. It's a teachable answer. Okay. So if I say 1 over here, wrong. If I say 0 over here, wrong. That sort of thing, right? So I want you to remember that, yeah, it does look similar, but it's totally different kind of deal. Very different kind of deal. Today, if I'm going to do this, I'm going to end up with 2 groups. I can also call this group 1 and group 2, right? Group 1 and group 2. Okay, now here, be very alert with my next sentence. Now that I have done this, I have introduced the label. Okay, now this label is not very meaningful because it is 1 and 2. Even if I call it label kidney group and banana group, it doesn't mean anything. Okay, so in addition to making this partition between group 1 and group 2, I can memorize this pattern. And now, corresponding to this, I can use this as label, right? In which case, here's a key point. In which case, somebody comes in, tells me which seat he or she would like to sit in, right? That student comes in, I want to sit there. Thereafter, I would label this student banana. Okay, so the banana versus kidney came out of the data, came out of nowhere, came from the data. But once you establish that, I can use it as a template, right? But this template wasn't there before because there's no distinguishing between black over here and black over there. So now there's implicitly, it's as if I'm doing this as well. Okay, but even if I'm doing this, I'm doing the classification, but it's not a real classification problem. You know, it's actually a real classification problem in a biology sense, because literally biologists, that's what they do. Okay, they get species and they make the taxonomy. So this is a little bit like creating the taxonomy. Okay, but in terms of data science, this is not called classification problem. It's called, it is considered a classification technique in the sense, but that's only possible because the previous distribution gave me the organizing principle to say, yes, there are 2 types of students in the world. There are the kidney students and there are the banana students. And so when the new student comes and say, I want to sit there, I say, I know, you're a kidney student. You belong to this group, right? Okay, so you understand now, okay? Another point, final point, to, again, this is a look back point. The difference between the previous class and this class is, by nature, this thing can be incomplete, right? Because you can have something like girls that sit here, right? Whereas here, you can establish a hard boundary of this here. Because you have real data, you say this is group 1, this is group 2. In fact, you don't have to say anything very much yet about here. Okay, so that's when you have uncertainty. But with respect to the data set you have, definitely this is 1, this is 2. There's no mixing. Okay, right? Because after all, I'm introducing the separation. Okay, so if I'm introducing the kidney group, there's no point saying this is a kidney, but hey, you are part banana, you should be there, but you over here. No, there's no point, right? Because after all, this is arbitrary designation. This is called cluster analysis. Okay, just like probability model gives a mathematical coverage of where you expect to find data. Okay. Now, I keep saying where you expect to find data. Data is fixed, it's found. What I mean is where you expect to find similar variable in the future, right? What we call random variable, or, so unseen data, okay? So that's what we want to do. Okay. Okay, you agree with me? This is called clustering analysis, right? And it's done in an unsupervised way. Why? Oh, think about it. You can imagine, you can imagine that this is a time of the day or something, and this is something like the sound, okay? And the baby just, this is a bad example, but the baby in an unsupervised way understand morning, day, and night. Okay, so knows morning, day, and night. It also understands loud and soft. And there are two groups of visitors to the hospital. There are people who came to come late, like this. You see what I mean? So your baby is learning to make association between two groups of visitors without you telling. You see what I mean? So that's why it's called unsupervised. It's unsupervised. There's no label. Hey, these are the night visitor. These are the day visitor. This is a loud visitor or soft visitor, right? There isn't. But your baby makes that grouping. Okay. Right. Okay. Oops. Forgot to ask you to take a picture. Okay. So that's what we want to do. Okay. That's what we want to do. Now, let me ask you, how would you do it? Well, obviously, the word, it's in the word, right? It's a cluster of data. It's a cluster of data. So how would you do this? How would you cluster the data? You would say something like, well, it's close together, right? Does that make sense? Make sense? By the way, this notion of closeness, keep that in the back of your mind. I'm going to come back when we talk about ChatGPT. This idea of closeness. Okay? Right now, you are closeness. So one of the method is based on literally closeness. Okay. So I would define, let's say I'm, a priori. Now you see an algorithm that you can say, I want this to be a very rough grouping. So group of two, I want it to be very detailed, in which case I may say, oh, there's one kidney, and actually it's an apple and a pear. So a three grouping, okay? The point is, the grouping can have, any number of groupings. But let's say I agree on two grouping. How would you go about drawing this circle? By the way, drawing a circle is drawing a curve. Drawing a curve is mathematics, right? So I just told you I don't want to do mathematics, okay? So this circle around you is kind of conceptual circle, okay? It's not like in statistics, right? In statistics, if you say you're sitting in a circular a radius or ellipse, I can draw ellipse with mathematical equation. Okay, in fact, that's what the multivariate normal distribution is. It's drawing ellipses in layers. Well, that bunching up into a kidney shape and banana shape is conceptual. So how exactly do I make the partition? So what I do is to say, okay, well, here's the data. Now I'm going to talk very quickly. Okay, I'm going to talk very quickly. The idea is very simple. Okay, I start randomly. Okay, right? And I measure the distance. Who's closest to blue? Raise your hand. Who's closest to red? Raise your hand. Raise your hand. Okay, so the one that's closest to blue, go to the blue. The one that's closest to the red goes to the red. Now, once you say, okay, these are the blue, go to the blue. The blue dot itself has to move closer to the group, right? So once this guy raise your hand, oh, okay, so you're closer to me, I go closer to you. Oops, sorry. I go closer to you. Okay, same thing with this red thing. Oh, so you closest to me, I go closer to you. Keep doing this for a while. Eventually, what's going to happen is, this is where you end up. Okay. And in a way, that thing is defined by the average of the coordinates. So if I can take all the coordinates in x1, okay, average it, and coordinate in x2, average it for this group, not the whole group, not the whole class, but for this group, I get a point. And that's kind of like at the center. Now, because center means it's kind of like center of a circle, but what's the center of a kidney? It's kind of like hard to say. So they use a new word called centroid. Okay, just come up with new word. It's centroid, it's central-ish. Okay, so that we call that a centroid. So basically, the result of this is an algorithm. Again, remember the difference between machine learning and regression equation. Regression equation, you end up with a formula. Machine learning, you have some kind of implicit mapping between X and Y. Same here. If it's statistical modeling, you have a mathematical description of this circle. Here, you have iterative process. Like it's probably, you know, akin to gradient descent. In fact, it's very close to that, right? Although it's not spoken of in that way. At the end of the day, what's going to happen? You don't end up with a mathematical description at all. You don't. You actually end up with 2 points and a list of members. The kidney is represented by the centroid and the list. All these guys belong to kidney. All these guys belong to bananas. There's no mathematical equation left at the end of that analysis. Okay, right? However, again, what if I have a new point? Then, okay, so if you did this once, we call it like once and done. Okay, do it once, done. But if I want to do this once, but hey, there's a new student coming, I don't want to put the new student and redo the whole analysis. I could, right? It's like saying that ChatGPT has trained for 8 hours using $1 billion worth of machine, right? And you want it to read another page of essay and retrain. Is it going to do that? No, it's not going to, right? Same, imagine, right? Imagine if this is a class and I have 50 more students coming in. Yeah, it's worth it. I add 50 more students and I redraw the grouping. Okay, but if only 2 students comes in, is it worth me redrawing the grouping? No, I'm just going to fix the centroid representation, right? Now I would do classification. Does this student belong to the kidney group or banana group? Okay, so this is what I call learning the partition. Okay, learning the cluster, learning cluster. So this becomes classification problem. But technically, it did not start out as a classification problem. And that's a subtlety that's very hard to explain, but I hope you with me. Yeah, because the kidney and banana did not come with you. When the room was empty, when you walk in, you had labels like boys and girls, but you didn't have labels like banana or kidney. It's only when you sit that I call you group 1 and I nickname you kidney. And here I call you group 2 and I nickname you banana. There's no intrinsic label, right? So it can't be a supervised learning model. However, when a new student comes, yeah, then it becomes like a classification problem, as if you're using the supervised learning model. Okay, this guy, yeah, he wants to sit here. Okay, then he is a banana. He wants to sit there. Okay, he's a kidney. Okay, but that's not there before. That's not there before. Okay, so something like now the reason I did this was because one. In Mathematica, you can do it both ways. You can do this thing called fine cluster, and I'm hoping I'm doing this more smoothly than yesterday. Instead of going back and forth, I'm just going to tell you first and I'll show you. So fine cluster is like, yeah, list this one group, this list another group. The other one is something like cluster classify or something. okay? And you put in the data. And what you get here is a partition. So this group, and if you have more than group, what you get here is an F, it's a function. And that function would give the label like 1 or 2 because it's automatically labeled 1 and 2. It doesn't give the name, okay? So I don't know what's the naming convention. Maybe the largest group gets the number 1 or something like that. Anyway, so if I throw this data to a Mathematica and say, find cluster, it's just going to list the students. Let's say you are identified by ID. All the ID of the students here in the kidney group is 1 bracket. Here's another bracket. So it's open bracket, you guys, close bracket, comma, open bracket, you guys, close bracket, close bracket. That's the output, okay? But if I say cluster classify, then it builds a function. And that function would look at you and say 1, 2, 1, 2. Somebody else come in, 2, 1. Does that make sense? Okay, that's it. It's easy as it gets. However, is life going to be easy? Well, definitely not. Otherwise, you're not. Why are you here? Life is not easy. Life is not easy. Right now, you have X1 and you have X2. You don't need machine learning algorithm. You don't need Mathematica to draw kidney, to draw banana, right? You can manually do it because what's the word? You can eyeball. You can literally eyeball the problem, okay? By the way, that's a word I use to communicate to my team when I say something that can be done in a humanly possible way because it has lower dimension. You can eyeball it. Problem is, you can only eyeball how many dimensions? Well, at most 3. You can do this kind of like scatter plot in 3 dimensions, right? And sort of like twisting the interactive visualization around, and you can do that. You can eyeball in 3 dimensions. You can eyeball in 2 dimensions. You can eyeball in 1 dimension. By the way, that's how I give grades. Okay? It's clustering in 1 dimension. Because the class is not big. And you guys are not homogeneous. If you guys were homogeneous, this is what, okay, this is kind of sidetrack, but it's also relevant. Okay? Okay, this is raw grade. This is raw grade, okay? Most of you guys are kind of average. Some of you are really good, so bad. Some of you are really good, right? This is what grading on a curve means, okay? I put you guys on a histogram, basically looks like this. Yeah, that's called grading on a curve, right? And I put, say, 10 percentile and 20 and this and something like that, right? So something like this would be A student, B student, C, D, F, right? That's called grading on a curve, okay? That's like height, something that's very normally distributed, okay? But you think, I've been here for what? This is my 3rd year with Basai, I think. I've never seen this. So you guys are not normally distributed in your performance, okay? You know what you look like? Yeah. There are a few of you over here, okay? There are a few of you, and usually there's a gap, and there's a little bit here, maybe a larger group, and maybe there's a little bit of smaller than this, but larger than that, and okay, it's a little bit like that, okay? Basically, your grades cluster in 1 dimension, okay? So if I were to do a histogram, it's gonna look a bit like Okay, it's not going to be a normal curve. So what happened? This guy gets an A, gets a B, a C, and it's his F or D, whatever. Okay, that's Basai students are really like that. Okay, they're really outstanding student who really pays attention, and there are, excuse me, Loi Toi student whom I don't know how we got them here, but somehow they got through to the admin. Okay, but they're not many. In fact, there are very few failing students. You know, students who always show up late, no homework, doesn't do anything. Very few. So maybe this is too many. Just maybe two. It tends to be like this. This is my observation. This is not always true. This is the smallest group. This is larger. This is larger, and this is largest. I don't know why. That's what I tend to see, by the way. Okay. So I can't put you guys on a curve. So most of you guys are B's. Some of you guys are C. A bit less of you are A. And then very few of you are, you know, the other way, all the way back down. So how do I grade you guys? I literally put the raw grades. And this is very objective, right? Nobody can say, you know, I favor this guy or that guy, or, oh, I should get it. No, I literally put you in a cluster. Now, technically, there is this thing called outcome-based education when you have a external standard of, you know, if you pass this, you should get an A. Well, in a lot of class, there's no external standard. It's not like running, okay? So it's not outcome-based in that sense. So you can't do that. So you have to basically assign empirically, except I don't do it with a normal curve, right? I don't do it with a normal curve. And if I I don't do it with a normal curve. I use clustering. So I put the raw grades and it's a fine cluster, right? And then that's it. That's your grades. Yeah. Okay, so that's one dimension. Okay, the reason I use Mathematica fine cluster for your grade is because I want to be quote unquote objective, right? I don't say, oh, I know this kid and he's kind of like on the borderline. I really like him. No, this is mathematically defined. It's algorithmically defined. But if you ask me, can I eyeball it? Yeah, easy, right? One dimension is very easy to eyeball. Two dimension is also easy to eyeball. Three dimension, a little bit trickier. Well, here's life. You will never, ever work with three-dimensional data in any significant sort of way, okay? Unless you're literally doing a distribution of a map or something, a GVI, okay? If you're talking about characteristic, okay? Imagine, I don't care what innovation product you have target groups, right? Okay? So think of, well, I'm going to put this in marketing term, market segmentation. Okay? Old style market segmentation have predefined labels, right? I'm going to target retiree. I'm going to target young, affluent people, right? Or whatever. Okay, I'm going to target salary earner. Oh, these are predefined labels, okay? And that's what old school marketing used to look like. Okay. Nowadays, no. Nowadays, my client base consists of 2 million people. For each person, I have age, education, sex, location, like urban or rural, all kind of stuff. Salary, okay? Outstanding debt, okay? Everything. Balance sheet, because I usually do with banks. So imagine that all my 2 millions have 20 numbers. Every one of my 2 million customer, actually when I was working bank, it was 4.5, right? I think so. Yeah. But different portfolio have different size. I think the largest was 4.5 we were working with. Anyway, let's say millions, okay? Just 1 million, just to be rough, okay? Every million customer, each one of them has 8 numbers. Okay, age, whatever, quantifiable. Again, this can be from nominal scale, ordinal scale, interval scale, ratio scale. But in a way, I can put numbers to them. I can put numbers to them. And there are 8 each. So what I'm talking about, when I talk about, I want to segment my market group. Let's say for the purpose of discussion, I want to divide into 5 groups because I have 5 heads of the department or something, okay? Like 5 sales department. So they can focus on different characteristics. So this is a very realistic way. Now, consider the unrealistic way, okay? Unrealistic way, number 1. All my 1 million customers are the same. All 1 million customers are the same. I divide them by 5 groups. Well, basically, I take the first 200,000 and the second 200,000, the third 200,000, and I say, okay, you take this, you take this, you take this, you take this, you take this. Okay, everybody's the same. Okay, number 1. Number 2, everybody is different. So I look at you individually. That's also not possible. That's, atrocious, right? You have 1 million customers. You can't individually customize. So old school customization is, okay, I have 1 million customers. They're not all the same. Some are retirees, some are affluent young professional, some are small business owner. But those are pre-defined label. Okay. Now, the clever way is to say, based on 8 statistics that I have on each person, what is the natural clustering? Okay, what's a natural clustering? And this is very difficult. Okay, now, before I go to that, let me say something that I think I I definitely have. Remember that I told you about using this centroid to locate the distance? Okay. Again, I don't want to go back and forth because it takes a transition time, but I'll show you later after the break. What if my data looks like this? Okay. Let's say these are location. You can think of it as pinpoint for a house or something like that. What do you think is happening here? The answer is there's a river separating them. And these are people who want to live, on a riverbank, right? Based on that, if I use a distance, what would happen? I would have one centroid here and one centroid here, right? However, this is not natural because the natural thing is I should do this. Assuming that there's no bridge, okay? There's no bridge. Okay, so this is kind of like, so this clustering makes sense, right? Because basically there's one West Bank community and one East Bank community, right? If I use that same technique, I'm going to have one here, and the centroid somewhere in the middle of the river. That's not good. So again, I just want to emphasize that, even in 2 dimensions, it's not straightforward, right? Not straightforward. This thing, by the way, the previous thing was called distance-based clustering. This here is also distance-based, but is contiguous distance. Basically, distance from house to house. Okay? So basically, you grow your cluster based on if you can touch hand. And this makes more sense. And in this case, it's kind of like density-based because, there's a density here. Because if you did this, this guy are closer together than this. And yet, in a way, house by house, if you want to travel one house at a time, you can get from here to here. You can't get from here to there because there's a river and there's an alligator in it. Okay? Right? So it's contiguous kind of closeness. We call it density based. Okay? So I should have mentioned that earlier, this example. But anyway, can you imagine something like this in higher dimension? Wow. Imagine a snake in 3 dimensions and you sort of like coil them up, right? And now snake in 8 dimensions. So definitely, this is not something you can do manually, okay? Old school customer segmentation, how do you do it? You make a line, right? Right? How do you say somebody who's a retiree over 60, right? How do you say somebody's affluent, income above whatever? So basically, you just do this kind of thing, right? That's very bad, okay? That's very bad. So you're going to end up with something like this partition. Right? Because you do this cut, you know. So maybe rich, famous, not so rich, not so famous, not poor, and not famous at all. Something like that. Okay? So it's this kind of rectangular cut. Doesn't make sense. Okay. Okay. So I want to show you, right? First of all, again, let me just roughly say there are 2 modes of running, 2 modes. Once and done. And then let's learn the partition. Yeah, 2 modes, right? Also, there are 2 schema. I'm going to call it schema. Schema is kind of like organizing principle. What do I mean by closeness? If I mean by global distance, I'm going to call it distance-based clustering. If I'm going to go by this kind of like micro distance, house by house, so as long as there's a contiguous mass that's densely concentrated, that shape can be like a snake, and this other shape can be like a snake, and the tail of this snake is close to the tail of that snake, but it's not connected, right? The tail here is actually connected to the head. That tail is connected to that head. So it's not the global distance, but kind of contiguous distance. Okay, we'll call that density based. So there's 2 modes, and there's distance base, and there's density base. Okay. Now, notice that you will never end up with one cluster. With traditional statistic, that's what you probably like. Okay, just describe where the data is, 1 ball in the middle. Okay, in this case, you never have 1 cluster. It's never interesting to say 1 cluster. It's never interesting because you're not adding any information, right? So if you have 1 data set that looks like a snake and you give it a shape, yeah, you can say that the shape is the snake, but you know, there are better way of describing that. So what I'm talking about here is the information is not just shape, but shape of clusters. And in fact, once you get to the shape of the cluster, you don't really care about the shape. At the end of the day, you only care about the cluster, right? Okay. So even though I said in the beginning that we're talking about information, put data into shape, once we get to the shape of kidney and bananas, really, I don't really care about the shape of the kidney or bananas. All I care is that 1 group cluster together, the other group cluster together, okay? So we kind of abandon that notion that data has to fall into this figure or whatever, okay? So the focus basically is on basically creating segmentation, Okay, segmentation in your mind, segmentation in a high dimensional space, segmentation in the mind of the computer. Okay, so when we come back, let's take a 5-minute break. When we come back, okay, I will show you. Okay, actually, no, don't go yet. Don't go yet. Don't go yet, because when I go back, I want to go to that computer, so I don't want to come back. So I have one more thing to cover that I'm going to use the board, so don't go yet. Okay, so the data is in dimensional n, which is bigger than 2, let's say, okay? Much bigger than 2, right? If it's 4, maybe you can do 2 at a time, maybe, okay? So it's much bigger. That's the whole problem, okay? You have, let's think of strategy, 2 strategy, okay? You know that you can eyeball 2 dimension, okay? You can eyeball 2 dimension, but you can't eyeball 20 dimension. Computer can eyeball 20 dimension and create the partition. Okay. Let's imagine that you're working for a dictator. A dictator, you go to him and say, your population has 8 dimensions. Okay. Salary, income, all kind of stuff, 8 dimensions. But the dictator say, I can't imagine 8 dimensions. And bangs his hand on the table and say, I want you to show me my population in 2 dimensions. He forces you. He forces you to show your dimension in 2 dimensions. Now, just for visualization's sake, okay, you go back and say, okay, fine. We have 8 dimensions. So let's give an interactive visualization, right? X1 versus X2, X2 versus X3. That would be what's called a scatter plot. Okay, that would be what's called scatter plot. However, what's wrong with scatter plot? If you say this is X1 versus X2, look at me. Okay, and this is X3 versus X4. Okay, my question is, can you eyeball the clustering? Can you eyeball the clustering? Yes, because it's 2 dimension. However, you'd be wrong, because this clustering here that you can eyeball and this clustering here may not be the same entities, right? So you can't do this independent study, right? Because these 2, okay, here's a group, right? And here's another group. However, look at me. Okay. However, if you look at this guy, in dimension X3, maybe this guy is over here, but this guy is over here. So the partition with respect to X1 and X2 and partition with respect to X3 and X4, different. So you cannot do this. So you can't humor that dictator by doing 2 at a time. And this is what scatter plot is done because I want to understand the data, and that's useful. But for this purpose of grouping the population into 2 groups, that's not a doable thing. So somehow you have to rely on the computer to do the 8-dimensional clustering. But once you do the 8-dimensional clustering, somehow you create, and the word is projection. I project the data from 8-dimensional space in 2-dimensional space. Okay? And I show the visualization to the dictator. Is this good? Yes. Because hopefully, if it has done its job, in 2 dimensions, there'll be a cluster of population here, and there's another cluster of population there. And they're separated, not in 2 dimensions, they actually separated in 8 dimensions, but I show them in 2 dimensions. So, well, actually, if I show them in 2 dimensions, my question is, what's this? I don't know. What's this? I don't know. It's not X1. It's not X2. It's not X3. It's not X4, 5, 6, 7, 8. It's a combination. It's a mix of that. In fact, it's some kind of weird amalgamation of all the dimensions. Except once you have this weird amalgamation of 8 dimensions, but you don't amalgamate to 1 dimension, you amalgamate to 2 dimensions. But these are completely artificial dimensions. So I'm going to say, I'm going to show this in A1 and in A2, where A1 is kind of a mix of 8 dimensions and A2 is a mix of 8 dimensions. Does that make sense? Okay. It's artificial, meaning there's no unit. There's no unit, but it's completely valid. Okay. This exercise, okay, is also done using, well, it's also considered part of bigger umbrella. It's done using unsupervised learning technique. And because you're reducing, you're projecting, but you're not projecting from 8 dimension to 9 dimension. You're projecting from 8 dimension to 2 dimension. It's a downward projection. We call this dimensionality reduction. So in unsupervised learning, as in my book, unsupervised learning will separate into cluster analysis, which is what we talked about for the most part. And the second part is called dimensionality reduction. Now, as you go to a break, you will have the impression that this dimensionality reduction is just a visualization exercise, right? It's just a visualization exercise. However, okay, let me leave you with a thought, and I'll give you the answer when we come back. Okay. Okay, this is a road. This is a road, right? It's a road. This road, well, it doesn't go uphill, downhill, just flat land. What dimension is it? 2 dimension, right? North, south, east, west, right? 2 dimension. But on this road, I'm going to put little houses. Actually, I can put streets or whatever, right? So this is /1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Here's my question. Do the houses live in 2 dimensions? Actually, from a street address point of view, it's only 1 dimension. It's only the first, second. Basically, you need 1 number to get to the house, right? If you're flying a helicopter and you want to land, yeah, you need 2 dimensions, right? But if you're driving, you are constrained by the road to go from 1 house to the next. So you only have 1 degree of freedom. So it is actually 1 dimension. Now imagine like this, except instead of houses, you have data. It's actually possible that even though you have 8 dimensions to describe your data, the 1 cluster, not multi-cluster, just the 1 cluster description of it, live in a lower dimension. Does that make sense? So in that case, dimensionality reduction would be good. The downside is, again, dimensionality reduction means you have no understanding what the reduced dimension is, right? In this case, you happen to know what it is because it's addressed along the street. So yeah, you can imagine that. But imagine that in 8 dimension, the population is not scattered kind of like homogeneously in 8 dimension, but it's kind of like living along this sub dimension. Technical word for it is called data manifold. Okay, don't have to memorize it because technically this word gets abused a lot, but it's a subspace, so to speak, right? Think of this. This is like a subspace. The whole space is 2-dimensional, but houses cannot live anywhere. House can only be on the road. So this is a 1-dimensional subspace of a 2-dimensional space, right? So I would call the house 1-dimensional data manifold. Okay, so this is more correct way of representing data because there's no real degree of freedom. I say, oh, you know what? I want to build a house here. No can do. No can do. You're actually not allowed to go off grid, basically, right? So you have less degree of freedom. Well, in a lot of problem, if you have 8 variable, but internally there's actually 5 degree of freedom, that's what dimensionality reduction comes in. Okay. Now, technically, nobody knows. Nobody. Well, there's some tests. But I'm sure. But nobody can really say, "Hey, this thing lives in 8 dimensions, but actually, it occupies only 4-dimensional subspace or 4-dimensional manifold." Because after all, you can't see 8 dimensions. How are you going to know that, right? Well, this you can see, but in 8 dimensions, you can't. So this problem of dimensionally reduction, conceptually, I hope you understand. Practically, it's a matter of experiment. In fact, I keep saying this. Data science is a science because it's an experiment. Okay. So it's almost like you're given a data in 8 dimensions. Maybe it actually lives in 3 dimensions or 4 dimensions. So let's find out. Do you lose information, basically, right? If I reduce this to just one number, do I lose any information? The answer is no. Because as long as you know, first house, second house, and you're driving on the road, you can find your house, okay? Right. So you can think of dimensional reduction as a more general thing. Now, when we come back, we're going to do 2 things. Okay, I'm not going to take break between because we're quite packed. So, you know, do your business. First thing, I would do all of this, clustering, dimensional reduction, demo it on a computer, right? And then it turns out that this dimensionality reduction is very exciting. This very concept, if you can picture that in your head, yeah, the idea that data live in some kind of subspace and you can actually go to artificial space and it's a better description. If you have that sort of like in your mind, I'm going to implant this in your brain as you go to the break. This will be the key to understanding, well, ChatGPT, large language model.